The workshop was silent except for the soft scraping of metal tools. November 1944. A Japanese Army Air Force engineering facility somewhere on the home islands. A group of senior engineers gathered around an object that had been transported under guard across the Pacific. It was an aircraft engine, specifically the Pratt Whitney R-2800 Double Wasp, the power plant of the American Vought F-4U Corsair fighter that had been terrorizing Japanese pilots across the Pacific for over a year. The engine had been salvaged from a downed American aircraft. Its cylinders arranged in a double row of 14 cylinders total. Its displacement nearly 2,000 cubic inches. Its rated output, according to American specifications, 2,250 horsepower at maximum military power. The Japanese engineers who examined it that day were among the finest their nation possessed. Men who had spent careers understanding aircraft engines. Men who had designed the Sakai engine that powered the Zero fighter. Men who had pushed Japanese engineering to the limits of what was possible in 1944. What they discovered as they began disassembling the R-2800 would challenge every assumption they held about American industrial capability. They had expected to find clever engineering, perhaps some innovative solutions to specific problems. What they found instead was something far more disturbing. They found mass production at a scale and precision that seemed almost incomprehensible. They found materials science that suggested access to resources Japan simply did not possess. They found manufacturing tolerances so consistent that individual components appeared virtually identical. They found an engine that represented not a breakthrough in engineering theory, but a breakthrough in systematic industrial organization. The disassembly continued for weeks. Measurements were taken, materials were analyzed. The findings were compiled into reports that moved up the chain of command. The conclusion was inescapable. Japanese engineers recognized that the R-2800 represented American industrial power concentrated into a single mechanical object. The engine was not just more powerful than Japanese equivalents. It was more reliable. It was more precisely manufactured. It was more readily maintained in field conditions. It represented an approach to aircraft engine design that prioritized production at scale over pursuing theoretical maximum performance. The psychological impact on Japanese officers who read these reports was profound. If American industry could produce engines this sophisticated in these quantities, what did that say about American capacity in weapons systems they could not examine? If you are enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The story of the Pratt Whitney R-2800 begins not with the engine itself, but with American industrial philosophy in the 1930s. American aircraft manufacturers faced a fundamental challenge. Engine power was increasing rapidly. Airframes were becoming faster. Weapons were becoming heavier. The demands on aircraft engines were escalating in ways that strained existing designs. Pratt & Whitney had dominated American aircraft engine manufacturing since the 1920s. The company had built its reputation on reliable, well-engineered engines that performed consistently across diverse conditions. The R-2800 project began in 1936 as an attempt to create an engine that could meet the demands of next-generation fighters. The Air Corps was projecting that fighters in the early 1940s would need engines producing 2,000 horsepower or more. Existing engines, like the R-1985, produced around 1,300 to 1,400 horsepower at maximum power. The jump to 2,000 horsepower represented an increase of nearly 50% in power density. Achieving this increase required solving problems across multiple domains simultaneously. Increasing displacement, increased engine size and weight. Increasing compression ratio improved efficiency, but raised combustion temperatures that required new materials and cooling approaches. Increasing rotational speed placed greater stresses on bearings and connecting rods. Each solution created new problems that required additional solutions. The traditional engineering approach in the 1930s had been to pursue perfection in individual components. Engineers designed components to exact specifications, tested them extensively, then gradually introduced the designs into production once reliability had been demonstrated. This approach produced excellent engines, but it was slow. The development cycle from initial design to introduction typically required 5 to 8 years. American manufacturers could not afford to wait. Fighter development cycles were accelerating. European manufacturers were introducing new aircraft at intervals measured in months, not years. American industry needed to compress development timelines while simultaneously increasing performance. The solution was not to abandon rigorous design, but to parallelize development efforts. Instead of sequential development where each phase depended on completion of the previous phase, Pratt & Whitney adopted simultaneous development approaches where multiple engineering teams worked on different aspects of the engine in parallel. The thermodynamics team focused on combustion efficiency and heat transfer. The mechanical design team focused on strengthening components to handle increased stresses. The manufacturing team focused on production methods that could reliably produce components to the required specifications. The material science team evaluated new alloys and processing techniques that could improve performance without requiring exotic materials unavailable in quantity. Communication between teams was structured but not rigidly hierarchical. When one team's work created implications for another team's designs, information was shared rapidly. Solutions from one domain were immediately communicated to all relevant teams. Problems discovered in testing were analyzed for systemic implications. If an issue was traced to material properties, material science investigations began immediately in parallel with continuing engine development. This organizational approach compressed development timelines dramatically. The R-2800 advanced from initial concept to first test engine in approximately 18 months, from first test engine to production engine in approximately 2 years, from production introduction to widespread fleet deployment in approximately 3 years. This timeline would have been considered impossibly aggressive in European aircraft engine development. It was considered routine in American industry during the 1930s and early 40s. The first R-2800 engines began testing in 1937. Early versions produced approximately 2,000 horsepower, meeting the design target. But performance gains in the engine specifications beyond basic power output revealed additional development opportunities. The engines ran hotter than optimal. Reliability remained borderline in sustained high-power operation. Overheating of certain components suggested internal aerodynamic flows could be improved. Rather than accepting the design as complete and moving to production, Pratt & Whitney pursued continuous improvement. Development models were modified to test solutions to identified problems. Modifications that proved successful were incorporated into subsequent production batches. This meant that R-2800 engines built in 1939 were noticeably more reliable than engines built in 1938. Engines built in 1940 were still more improved. The process did not stop. Throughout the war, R-2800 engines were continuously modified and improved. Cylinder head designs were refined to improve cooling. Fuel injection systems were modified to provide better atomization. Supercharger designs were upgraded to increase high-altitude power output. Each modification was tested, validated, then rolled into production. By 1944, production R-2800 engines were more powerful, more reliable, and more efficient than engines built just 2 years earlier. The manufacturing infrastructure that produced these engines was equally impressive. Pratt & Whitney operated manufacturing facilities in Hartford, Connecticut, and New Haven, Connecticut. These facilities were not small, specialized shops producing aircraft engines as artisanal products. They were massive industrial complexes employing thousands of workers, operating assembly lines, and utilizing precision machinery that had been purpose-built for aircraft engine production. A single Pratt & Whitney facility in New Haven could produce 400 engines per month by 1944. 400 complex machines, each containing over 2,000 individual parts, each requiring precision manufacturing to tolerances measured in thousandths of an inch, each tested to ensure performance met specifications before leaving the factory. The scale of this production was enabled not by manual labor, but by systematic application of manufacturing engineering. Jigs and fixtures were designed to position components for machining within extremely precise tolerances. Machine tools were selected and configured to achieve the required precision repeatedly, shift after shift, day after day. Quality control checkpoints were established at critical manufacturing steps to catch problems before they propagated. Statistical process control techniques were applied to monitor manufacturing consistency and identify when process drift indicated adjustment was necessary. Workers were trained in standardized procedures that ensured consistent execution. When procedures were modified to incorporate improvements, all workers received updated training. The result was that engines produced in different facilities on different shifts by different workers were virtually identical. This consistency was not achieved through handcrafted excellence, but through systematic engineering of manufacturing processes that made excellence routine rather than exceptional. Japanese aircraft engine manufacturing in the 1940s operated under fundamentally different principles. The Sakai engine that powered the Zero fighter was an excellent design. Japanese engineers had optimized every component for maximum performance. The engine produced approximately 900 to 1,000 horsepower, depending on variant and atmospheric conditions. The designs were sophisticated and well-engineered, but production remained primarily craft-based. Skilled workers assembled engines in dedicated workstations. Components were hand-fitted to achieve proper clearances. Adjustment and tuning were performed by experienced technicians who understood the characteristics of individual engines. This approach produced excellent engines when performed by skilled workers, but was extremely labor-intensive. A single Sakai engine required approximately 200 hours of skilled manufacturing labor. Production rates were consequently limited. Japanese factories producing Sakai engines were manufacturing dozens per month, not hundreds. Quality control was based on inspection of finished engines rather than statistical process monitoring of manufacturing steps. If an engine failed testing, it was returned for rework. This required that the technician who built it disassemble the engine, identify the problem, correct it, and rebuild the engine. The process was extraordinarily labor-intensive. By 1944, Japanese aircraft engine production was severely constrained by labor availability and manufacturing capacity. Raw materials were increasingly scarce as American naval forces strangled Japanese maritime supply lines. The precision machinery required for manufacturing had to be imported or manufactured domestically at great cost. Modifications to designs took months to implement across production facilities, because each facility was essentially independent, with limited coordination for production engineering. The technical specifications told only part of the story. When Japanese engineers began measuring the R-2800's components, they discovered details that suggested a level of manufacturing sophistication that transcended simple technical advantage. The cylinders, for instance, were manufactured to tolerances of plus or minus 0.005 inches. This was approximately 1/10 of a millimeter. Achieving this precision consistently across 14 cylinders required machine tools of extraordinary capability. The boring machines that produced these cylinders had to maintain dimensional accuracy across extended production runs without drift. This required precision positioning systems, rigid machine frames that minimized deflection under cutting forces, and cutting tools that maintained sharp edges despite removing metal continuously. The machines themselves represented significant engineering and manufacturing investment. Each boring machine cost thousands of dollars to design and build. Pratt and Whitney operated dozens of such machines in facilities dedicated to cylinder production. Japanese manufacturing equipment in 1944 was far less sophisticated. Cylinder boring was performed on universal machine tools that required skilled operators to make constant adjustments to maintain tolerance. Dimensional variation between cylinders was greater. Each cylinder required individual measurement and correction. The result was higher manufacturing labor per cylinder and lower production rate. More significantly, dimensional variation required assembly technicians to hand-fit cylinders to individual pistons, a labor-intensive process that could not be eliminated through process improvements because the dimensional starting point was inconsistent. The piston designs revealed additional sophistication. American pistons incorporated cooling galleries, internal passages where hot oil could circulate to carry heat away from the combustion chamber. These galleries were created through precision casting and subsequent drilling. The cooling galleries reduced piston temperature and improved reliability in high-power operation. Japanese pistons lacked equivalent cooling features because the manufacturing precision required to create internal galleries was not available. The most efficient connecting rods were forged and machined from special alloys. American manufacturers had evaluated multiple alloys and selected materials that provided optimal combinations of strength, fatigue, resistance, and cost. The selection process involved testing candidate materials under conditions representing actual engine operation. Samples of forged material were subject to fatigue testing to establish failure limits. Specifications were written defining material composition, heat treat procedures, and machining tolerances that ensured consistent properties. Japanese connecting rods were manufactured from available materials using traditional forging and machining processes. Quality control depended on sampling and testing finished components rather than process monitoring. If a connecting rod failed during engine testing, it was returned to the manufacturer for investigation and redesign. The process was reactive rather than proactive, and modifications to improve reliability typically took months to implement across production facilities. The supercharger represented perhaps the most sophisticated component in the R-2800. Pratt Whitney used a centrifugal supercharger that increased intake air pressure at altitude, allowing the engine to maintain power output as atmospheric pressure decreased. The supercharger consisted of a precision impeller rotating at speeds exceeding 20,000 revolutions per minute. The impeller had to be manufactured with aerodynamic precision. Blade shapes had to match design specifications within tolerances measured in thousandths of an inch. The manufacturing process for supercharger impellers involved casting, machining, and polishing to achieve the required aerodynamic profile. Each impeller was dynamically balanced to ensure smooth operation at high rotational speeds. Imbalance at 20,000 revolutions per minute would generate vibrations that could damage the engine. American facilities maintained precision balancing equipment. Each supercharger impeller was individually balanced and documented. The process was labor-intensive but ensured reliable operation. Japanese supercharger development lagged significantly behind American development. Japanese engineers understood the aerodynamic principles of supercharger design. Designs were sophisticated and well-engineered, but manufacturing the designs presented challenges that exceeded available manufacturing capacity. Precision casting of complex shapes required excellent foundry technique. Aerodynamic machining of impeller blades required skilled machinists and precision machine tools. Balancing equipment for high-speed operation required specialized facilities. The combination of design complexity and manufacturing demands meant Japanese supercharger development proceeded slowly. The Sakai engine in 1944 was still using mechanical superchargers with relatively simple designs. Pratt & Whitney had advanced beyond mechanical superchargers to two-stage supercharger systems that provided more efficient pressure increase across altitude ranges. The R-2800 incorporated sophisticated fuel injection systems that injected fuel directly into each cylinder rather than using conventional carburetors. Carburetor systems injected fuel into the engine intake manifold, where it mixed with air before entering cylinders. This approach was simple and reliable but had limitations. At high altitudes where air density was low, carburetor systems struggled to maintain proper fuel-air ratios. During negative G maneuvers where aircraft nose pointed downward, carburetor-fed engines could momentarily stop feeding fuel as centrifugal forces moved fuel away from the pickup. Direct fuel injection solved both problems. Fuel was injected at measured pressures directly into each cylinder at precisely timed intervals during the induction stroke. The system required precision fuel pumps capable of maintaining constant pressure despite varying engine speeds and fuel temperatures. Fuel injectors needed precision calibration to ensure consistent atomization and combustion. Control systems needed to adjust fuel flow for varying atmospheric conditions and engine power settings. The system was complex and required sophisticated manufacturing to produce reliably. American manufacturers had developed these systems because the performance advantages justified the manufacturing complexity. Engines with direct fuel injection could maintain power in negative G maneuvers, where carburetor-fed engines faltered. Engines with direct fuel injection could maintain power at altitudes where carburetor-fed engines struggled. American fighter pilots consequently had reliability advantages that translated to combat effectiveness. Japanese aircraft manufacturers understood the advantages but could not manufacture the systems reliably. When Japanese engineers examined the fuel injection system on the captured R-2800, they recognized the sophistication immediately. The fuel pump maintained pressure to within tight tolerances. The injectors produced consistent spray patterns. The control systems incorporated mechanical feedback mechanisms that automatically adjusted fuel flow based on engine operating conditions. The design was elegant and apparently simple, but the execution required precision manufacturing at multiple stages. Most significantly, manufacturing these components required quality control procedures that ensured consistency. Fuel pump output had to be tested and verified. Injectors had to be tested to ensure spray patterns were uniform. Control system linkages had to be adjusted and synchronized. Each step required skilled labor and precision measuring equipment. Multiplying this across production runs of hundreds of engines per month required automated and semi-automated processes that Japanese industry had not developed. The bearing system revealed additional sophistication. The R-2800 incorporated sleeve bearings, precision metal sleeves that supported rotating shafts on films of pressurized oil. The bearings had to be manufactured to tolerances that ensured proper oil film thickness. Too tight and bearing temperatures would rise excessively. Too loose and thrust loads on the crankshaft would cause excessive wear. American bearings were manufactured to specifications that ensured optimal performance across the design operating range. Japanese bearings were manufactured using conventional methods that required hand-fitting by skilled assemblers. The process was labor-intensive and resulted in bearing characteristics that varied from engine to engine. This variation meant some engines ran with excessive bearing clearance that caused vibration and accelerated wear. Other engines ran with marginal clearance that generated excessive heat. Neither condition was acceptable for aircraft engines operating continuously at high power. Settings. The crankshaft itself was a marvel of precision, forging, and machining. The R-2800 crankshaft had to transmit over 2,000 horsepower from 7 cylinders, while withstanding stresses that varied cyclically with engine operation. The design incorporated optimal weight distribution to minimize vibration, while maintaining structural strength. Manufacturing required precision forging to produce the basic shape, followed by precision machining to achieve final dimensions and balance. Crankshaft balance was critical. Imbalance in a 14-cylinder engine rotating at 3,000 revolutions per minute would generate destructive vibration. American manufacturers dynamically balanced every crankshaft after finishing. Weights were added or material removed to achieve perfect balance within specified limits. Japanese manufacturers balanced crankshafts through static balance procedures that were less precise. Residual imbalance was tolerated as an acceptable manufacturing limitation. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The exhaust system incorporated sophisticated valve designs. The intake and exhaust valves were operated through cam followers and push rods driven by a camshaft. The valves opened and closed at precisely timed intervals to control intake of fuel and air mixture and exhaust of burned gases. Valve timing was critical to engine efficiency. Early or late valve opening or closing degraded performance. The cam profile determined valve timing through mechanical advantage of the cam follower and push rod linkages. American valve designs incorporated hardened valve seat inserts that resisted erosion from hot exhaust gases. The seats were precision manufactured and installed in the cylinder head with tight interference fits to ensure consistent contact. Valve stems were precision ground and hardened to withstand thermal cycling and mechanical erosion. The valve guides that controlled valve stem movement were precision bored to maintain appropriate clearance. Japanese valves were manufactured using conventional methods. Valve seats were not always hardened, allowing erosion that eventually degraded sealing surfaces. Valve stem clearances were greater, allowing more movement that increased noise and accelerated wear. The differences were individually small, but compounded together they reduced engine reliability and required more frequent maintenance. The cumulative effect of these design and manufacturing differences was dramatic. An R-2800 engine could operate continuously at high power settings, with reliability that allowed American pilots to operate aggressively without fear of mechanical failure. A Sakai engine required careful operation within narrow limits and regular overhauls to maintain reliability. American pilots could push their engines toward design limits. Japanese pilots had to operate well within safe limits to ensure reliability for combat operations. This difference manifested in combat performance. American fighter pilots could engage at full power for sustained periods, maneuvering aggressively and using engine power to accelerate or climb away from disadvantageous combat positions. Japanese pilots operating similar high-power settings risked mechanical failures that would force landing before reaching friendly territory. The result was that American pilots could exploit their aircraft's performance potential. Japanese pilots operated with artificial limitations imposed by reliability concerns. Reports from Japanese test pilots who flew captured American aircraft repeatedly mentioned that engines seemed to run smoothly, with mechanical precision that contrasted sharply with Japanese engines. Pilots noted that American engines delivered smooth power delivery without vibration. American engines started reliably even in cold weather. American engines maintained power output during combat maneuvering. Japanese test pilots understood these observations, reflected manufacturing quality differences, not design superiority. Lieutenant Commander Masao Kawauchi, a senior Japanese aircraft engineer who analyzed captured American engines extensively, submitted a detailed report to the Japanese military in 1944. Kawauchi had studied aeronautical engineering in Germany before the war and had returned to Japan with understanding of advanced manufacturing concepts. His report noted that American aircraft engine production represented systematic application of precision manufacturing at scales that exceeded Japanese industrial capacity. Kawauchi calculated that producing a single R-2800 engine required approximately 180 hours of manufacturing labor. This was approximately 10% of the labor required for Japanese Sakai engines. Multiplying across production volumes, American industry could produce approximately 5 engines for every single Japanese engine with equivalent manufacturing labor investment. This calculation assumed Japanese workers were equally trained and equally productive as American workers, which was not always the case. In many cases, American productivity per worker exceeded Japanese productivity because of superior manufacturing processes and equipment. Kawauchi concluded that without fundamental reorganization of Japanese manufacturing and access to advanced machine tools, Japanese aircraft engine production could not be significantly improved. The report was submitted to Japanese military leadership and noted for its pessimism. Officers reading Kawauchi's report could not accept conclusions that American manufacturing was fundamentally superior. Pessimistic reports were discouraged. Kawauchi was reassigned to duties that removed him from influence over manufacturing decisions, but the evidence was undeniable. By 1944, American aircraft were equipped with engines that were more powerful, more reliable, and manufactured in quantities that gave American aviation quantitative advantage on top of qualitative advantage. A single American fighter wing had more engines than entire Japanese air defense squadrons. American industry could replace damaged aircraft with new production within weeks. Japanese industry could not replace losses at equivalent rates. The R-2800 represented an asymmetry that could not be overcome through tactical innovation or pilot skill. Individual Japanese pilots might be more skilled than individual American pilots, but American pilots were equipped with aircraft that were more reliable and more powerful. American squadrons could maintain strength through replacement of losses. Japanese squadrons could not. American aviation could take risks because consequences of losses could be replaced. Japanese aviation could not afford losses and operated defensively to preserve remaining strength. The captured engine disassembly was completed in early 1945. Japanese engineers compiled detailed reports documenting the design and manufacturing characteristics. The reports circulated among military leadership and industrial planners. Recommendations for improving Japanese engine production were submitted. Most recommendations required investments and manufacturing reorganization that were no longer possible as American air superiority made industrial expansion dangerous. Factories producing advanced engines would have been high-value targets for American bombing raids. Japanese industrial capacity was already stretched thin. Resources and skilled workers were increasingly scarce as casualties in ground combat accelerated. The window for responding to technological inferiority had closed years earlier. In 1944 and 1945, Japanese could only document the gap that had opened. The ultimate significance of the R-2800 became apparent not through laboratory analysis, but through combat experience. By mid-1944, American F-4U Corsair fighters equipped with these engines were dominating Japanese aircraft across the Pacific. The Corsair was fast, powerful, and remarkably reliable. Japanese pilots who encountered Corsairs in combat reported aircraft that could climb away from engagement, dive to escape pursuit, and maintain high-speed maneuvers without mechanical failure. Previous American fighters had been competitive with Japanese aircraft through pilot skill and tactical advantage. The Corsair represented a different category. The combination of engine power, airframe design, and manufacturing quality created an aircraft that was superior across virtually every performance metric. Japanese fighters could not match the Corsair's speed at most altitudes. They could not outclimb the Corsair. They could not match the Corsair's diving speed because American manufacturing quality meant engines could withstand higher stresses. Japanese pilots recognized that conventional tactical approaches developed in earlier combat had become obsolete. The Corsair represented a technological advance so significant that tactics proven effective against earlier American fighters no longer worked. Japanese pilots adapted by attempting to use superior maneuverability to achieve favorable combat positions. But superior maneuverability meant nothing if the American pilot could avoid engagement through superior speed and climb. The frustration experienced by Japanese pilots was palpable in after-action reports. Pilots noted that American aircraft seemed to operate without limitation. American pilots engaged at full power without apparent fear of mechanical failure. American pilots could pursue Japanese fighters with aggressive maneuvering that Japanese pilots would not attempt because the mechanical stresses seemed unsustainable. The difference reflected the manufacturing quality differences that Japanese engineers had documented during the R-2800 analysis. By 1945, Japanese air defense operations had become exercises in futility. American fighters could penetrate Japanese airspace with impunity. They could operate at altitudes and speeds that Japanese fighters could not match. They could pursue damaged American bombers into Japanese territory and intercept them before landing. Japanese pilots were flying aircraft that had been in service for 2 to 4 years, suffering from mechanical wear and accumulated damage from previous combat. American pilots were flying aircraft with fresh engines that had been through controlled manufacturing processes. The maintenance situation illustrated the disparity starkly. American aircraft returned to bases after each mission, where trained mechanics performed inspections and maintenance using standardized procedures. Engines were replaced after specified service intervals, regardless of apparent condition. Worn components were replaced with new production parts that met manufacturing specifications. The result was that American aircraft maintained performance levels equivalent to new production throughout service life. Japanese aircraft were maintained by overworked mechanics, working with limited spare parts. Engines were operated until they failed, rather than being replaced at service intervals. Worn components were patched and coaxed through continued operation. The result was that Japanese aircraft performance degraded throughout service life. An aircraft that had been competitive when new became increasingly uncompetitive as engines tired and components wore. The divergence in aircraft performance throughout service life created advantages that compounded. American pilots flying fresh aircraft with reliable engines could take tactical risks. Japanese pilots flying tired aircraft with potentially failing engines could not. American formations could operate aggressively. Japanese formations had to operate defensively and conservatively. The difference in operational capability grew as the war continued. By war's end, Japanese air defense had essentially ceased. The combination of American numerical advantage, American technological advantage, and American industrial capacity to replace losses had proven overwhelming. Japanese air forces attempted to transition to kamikaze operations, accepting the loss of aircraft and pilots because defensive operations had become militarily irrelevant. The R-2800 engine had not caused this outcome alone, but it represented the concentration of American advantages in a single mechanism. The engine's power allowed the Corsair to outperform competing aircraft. The engine's reliability allowed pilots to push performance limits. The engine's consistent manufacturing quality meant every aircraft was reliable. The engine's production rate meant losses could be replaced. Each characteristic alone provided advantage. Combined, they created asymmetry that could not be overcome. When Japanese engineers reviewed detailed analysis of the engine in 1944 and 1945, they were confronting evidence that American industry had fundamentally out-organized Japanese industry. Individual component excellence was insufficient. Production at scale was necessary. Manufacturing consistency was necessary. Continuous improvement in production capability was necessary. Japanese industry could achieve all these things individually, but could not integrate them simultaneously at the scale American industry maintained. The R-2800 represented industrial power transformed into engineering capability, then transformed again into combat capability. The engine did not exist because American engineers were inherently more brilliant than Japanese engineers. The engine existed because American industry had been organized to translate laboratory research into production capability at scales that exceeded Japanese industrial organization. The manufacturing precision reflected not unique American skill, but systematic application of precision manufacturing practices that had been developed through decades of industrial development. American industry had been producing complex machinery since the 1900s. Machine tools, automobiles, and precision instruments had driven development of manufacturing techniques that eventually were applied to aircraft engine production. By 1941, American industrial infrastructure for precision manufacturing was mature and extensive. When aircraft engine designers needed precision components, facilities existed that could produce them. When manufacturing efficiency improvements were identified, capital investment could fund implementation. Japanese industry had developed precision manufacturing capabilities, but these capabilities were concentrated in limited facilities and limited fields. Aircraft engine manufacturing represented relatively recent development compared to American industry. The industrial base supporting advanced manufacturing was less developed. Capital investment in manufacturing improvement was constrained by competing demands. The result was that Japanese manufacturing could not achieve efficiency equivalent to American manufacturing. The technological gap that emerged during the war reflected these underlying differences in industrial organization and industrial development. Individual Japanese engineers were capable of designing sophisticated engines. Japanese craftsmen could produce engines of excellent quality, but Japanese industry could not replicate American manufacturing efficiency at scale. This was not a failure of Japanese capability, but a difference in industrial organization and development history. The implications were strategic, rather than merely tactical. Nations that could organize industry to produce advanced military equipment in quantity possessed advantages that tactical skill and courage could not overcome. The war demonstrated this with brutal clarity. American industry produced aircraft, weapons, and equipment in quantities that seemed almost magical to enemies struggling to maintain basic production levels. American industry could produce replacement equipment faster than enemies could destroy it. American forces consequently had confidence that losses could be replaced and risks could be taken. Japanese industry struggled to produce basic quantities of equipment needed for operations. Japanese forces operated with consciousness that losses could not be easily replaced. Japanese tactics reflected this consciousness, emphasizing conservation of force and reduction of risk. American tactics reflected different consciousness, emphasizing exploitation of advantages and acceptance of risks because consequences could be managed. The difference in industrial capacity consequently created difference in operational doctrine and tactical approach. When Captain Sanji Iwabuchi had gripped the rangefinder on battleship Kirishima's bridge months earlier, he believed that superior optics and superior training would determine victory. When Japanese pilots flew Zeros against American fighters, they believed that superior maneuverability and superior tactics would overcome American numerical advantage. When Japanese commanders planned operations, they believed that will and courage would compensate for material disadvantage. These beliefs were not irrational. They were based on training, experience, and culture that had served Japanese military forces well before the war. But the R-2800 engine represented a different category of advantage. It represented not incremental improvement but systematic transformation of manufacturing. It represented not one innovation but dozens of innovations integrated into a system. It represented not one factory but an entire industrial ecosystem. The engine could not be matched through superior training or tactical innovation. It could only be matched through equivalent industrial organization and manufacturing infrastructure, resources Japan did not have and could not develop during wartime. Japanese military leadership had understood the implications too late. The reports from engineers who had examined the R-2800 had been clear and pessimistic. American manufacturing capacity exceeded Japanese capacity by factors of 5 to 10. American technology was improving continuously, while Japanese technology struggled to advance. The gap was widening, not narrowing. The war would be decided not in combat between skilled warriors, but in factories between industrial systems. The lesson was bitter and profound. Individual excellence could not overcome systematic disadvantage. Courage could not overcome engineering. Will could not overcome manufacturing capacity. The Japanese Navy had been the finest naval force in the world in 1941. Crewed by professionals who had devoted careers to their craft. By 1945, that navy had been destroyed not by superior enemy courage, but by superior enemy manufacturing. The Air Force had been equipped with aircraft that were competitive in 1941, flown by pilots trained in tactics proven effective across years of combat. By 1945, those aircraft were obsolete, outmatched by American aircraft powered by engines that represented industrial supremacy. The R-2800 engine became a symbol of a fundamental truth about modern industrial warfare. Victory belonged not to the nation with the best warriors, but to the nation with the best factories. Technology mattered not as individual innovations, but as systematic integration across entire military structures. Industrial capacity mattered not as abstract statistics, but as concrete manifestation in weapons that worked reliably, performed as designed, and could be produced in quantities that exceeded enemy capacity. After the war ended, Japanese engineers who had examined the captured engine went on to shape Japan's industrial reconstruction. Lieutenant Commander Masao Kawauchi survived the war and became a consultant to American occupation authorities seeking to understand Japanese capabilities. His analysis emphasized consistently that technological inferiority had been inevitable given industrial organizational differences. His post-war career included advocacy for adoption of American manufacturing practices and quality control standards. The influence of engineers like Kawauchi contributed to Japan's post-war transformation into a manufacturing powerhouse. But that transformation took decades of development and reorganization that Japan did not have time to accomplish during 1944 and 1945. The war ended while Japan was still documenting the gap. By the time Japanese industry could have responded to the technological disparity, the war was over. American victory was not decided by any single factor, but by the accumulated weight of industrial advantage, technological advancement, and manufacturing superiority that the R-2800 engine represented. The Vought F-4U Corsair continues to serve as one of the most respected aircraft of the Second World War. Veterans of the Pacific Campaign speak of the Corsair's reliability and performance with appreciation that borders on affection. American pilots trusted their Corsairs in ways Japanese pilots could never trust aging Zeros. The engine that powered the Corsair had proven itself across years of combat operations, demonstrating reliability that reflected manufacturing excellence. Japanese pilots who encountered Corsairs across the Pacific recognized immediately that they faced an aircraft in a different category from earlier American fighters. The Corsair did not win the war through superior tactics or innovative design. It won through the accumulated advantage of an industrial base organized to produce reliable, powerful aircraft in quantities that overwhelmed enemy capability. The R-2800 engine was the visible expression of this industrial superiority. When Japanese engineers finally completed their analysis of the captured engine in early 1945 and compiled their reports, they were documenting the technological foundation of American victory. The reports gathered dust in Japanese archives as the war continued to its inevitable conclusion. By the time the war ended, Japanese military leadership had no resources to implement the recommendations the reports suggested. The opportunity to respond to American industrial superiority had passed. The story of the Pratt Whitney R-2800 engine and the Japanese engineers who examined it is ultimately a story about industrial organization. It is a story about how systematic approach to manufacturing can create advantages as decisive as any tactical innovation or engineering breakthrough. It is a story about how the future of warfare had shifted from battlefields, where warriors fought with courage and skill, to factories where engineers and workers produced weapons in quantity. The Japanese Navy, that had begun the war as one of the finest naval forces in the world, had been destroyed not by superior enemy courage, but by superior enemy manufacturing. The Japanese Air Force, that had begun the war with aircraft competitive with any in the world, had been reduced to irrelevance not by inferior pilot skill, but by inferior industrial capacity. The R-2800 engine represented the physical manifestation of this industrial transformation. When the war ended in 1945, American industry had proven that systematic organization of manufacturing could overcome any tactical disadvantage. American factories had produced weapons in quantities that seemed almost magical. American industry had continuously improved those weapons throughout the war. American forces had benefited from this industrial superiority, not in one campaign, but throughout the entire Pacific War. The lesson shaped military thinking for decades that would follow. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.